professor at the Institute of Photonic Sciences at Barcelona. He has a degree both in physics and in engineering from the University de Barcelona and also from the Polytechnic de Catalunya. He got his PhD in physics from the University of Barcelona, and then he had a postdoctoral stint with the group of Professor Nicolas Gissin in Geneva. He is today, like I said, an ICREA research professor at ICFO, the Institute of Photonic Sciences. His research activity spans foundations of quantum physics, quantum cryptography, quantum thermodynamics, and quantum optics. He is also an AXA chair in quantum information science in 2016. So without further ado, let me hand over the floor to Professor Acin. I request the participants to type your questions in the chat, and maybe we can have a Q&A towards the end. Thank you.
Okay, thank you very much for the nice introduction. I will now share my screen and we can start. Yes. So I guess you can see my screen and pointer, right?
Yes, that's right. Yeah.
Okay, good. So yeah, okay. Thanks for the introduction. Thanks for the invitation. So I'll tell you. So my talk, it will be about direction in which we are quite active at the moment, and that we somehow call network quantum information processing. So basically, we're interested in understanding what you can do with quantum networks. So so far, many say theoretical results in quantum information science were considering the typical scenario where there is Alice and Bob. Sometimes even multipartite, but you will see not the type of multipartite scenario that I'm going to describe here. So, but mostly they were considering, say, what I'm going to call point-to-point configuration, say Alice and Bob. So there was a situation in which, say, Alice was preparing states and Bob was making measurement, or the opposite. So if you think of a protocol like BBNT4, this is what is happening. So Alice is preparing some states and Bob is making some measurements. And I will be representing this generically as different preparations that I will label by X. And then you prepare the state rho X, depending on what you choose to prepare. And this rho X can be a qubit, QT state, well, depending on how many assumptions you want to do on this preparation. And then at the receiver station, you're making some other measurements that you label by Y, and you get the result B. And somehow this is what you see in the lab. So you see the probability of observing a given result B, depending on which measurements you implemented and which state was prepared. Or you also have this sort of, okay, maybe point-to-point configuration, not really, but Alice Bob mediated by a quantum source. Okay, there was a source that prepared a state of two particles, and these two particles were sent to two different locations. And again, you were making measurements on these particle states. So this scenario has been studied a lot, but now we want to go beyond that. I mean, for theoretical reasons, but also for experimental reasons, because now technologies are advancing, and now we have a situation in which we can consider networks. Sorry, just a second. I'm back. So we can consider networks in which we have different sources and quite good sources, say single photon sources, and we can have this. Say these are now the observers. They may receive states from different sources, and they can also make entangling measurements. Okay, so before they were just making single particle measurements. Now they may get different particles from different sources, and they can make entangling measurements on those. So they can even store quantum information for a while, because we have some decent quantum memories, and sometimes we can even consider a scenario in which they can make some simple quantum logic with these quantum particles. Okay, I'm not thinking of any quantum computer distributed quantum computation. I'm thinking of a more modest scenario in which, okay, you can prepare, say, 2-3 states that are sent to different nodes. Okay, here in this case it's 5 states, 5 maybe maximum entanglement states of 2 qubits, and they are sent, and you make these measurements. Okay, so we want to understand what you can get in this regime, and well, we also want to understand what will happen when you have a large network. But so I think at the moment we are more interested in what you can do with smaller quantum networks. But again, also the asymptotic regime is interesting. Okay, so this is a question that we care about, and also we also want to maintain this double focus on foundations and quantum information applications. Okay, so I think it's a nice situation in which you can, and this is also one of the goals of my talk. Okay, so I will tell you results on quantum foundation, but also results on quantum information science. So we want to keep this connection between the two aspects. Also, because if you really understand from a foundations point of view what makes quantum physics special, this is usually very relevant to make better quantum information applications. And the problem of quantum networks you can consider from many different perspectives and so we have different frameworks. In my case, I'm going to focus on what is called the device-dependent scenario. Okay, so this is a situation in which the modeling of your network is quite minimalistic. So I will put the nodes in my network as just black boxes that may receive particles from sources, okay? And they make measurements on these particles that they received and they get some results. Okay, these measurements may involve some non-complex operations on the particles they may have, but okay, they can do whatever they want with the particles that they receive. But at the very end, they produce classical output. And then the object that I will use to describe my scenario, my network, will be just the observed, what I'm going to say, the observed correlations, the observed statistics. So what is the probability of observing, say, result A1 on box 1 and AI on box I and AN on box N when they use the input X1, XI, XN. Okay, so these are just observed probabilities. And this is what I'm going, my description of the network is going to be through the statistics that is produced in the network. And this device-dependent scenario, you model, or basically you don't model the device producing the output given the input. So all your interaction with the device is through classical information, because if you think about us as observers, we interact with quantum systems classically. So we put some mirrors in some given positions, or we apply some light pulses, and we have a classical description of that. So we interact through classical information, and at the very end, what we observe is also classical information. Okay, and of course, all what might be behind the scenes can be quantum. Okay, this is perfectly valid. And in the device-dependent scenario, since these are black box, you don't make any assumption about the quantum process that gives rise to the output given the input. Also, I'm going to assume that these devices are separated. So what happens here is just given by a local description that takes place here. I don't know if there is something. Okay, well, let me just, I guess there's something in the chat, but I should ignore it. I will go on with my talk. Okay.
Yeah, please go ahead. It's just information to type questions in the chat. That's all. Go ahead.
Okay, okay, good. Let me just, I should. Okay. Okay, and in this connection between foundations, so what we want to do from a foundation point of view, we want to understand which correlations you can observe, and especially with no classical analog. And then from a quantum information science point of view, we want to explore these correlations with no classical analog for quantum information processing. And also one of the reasons why we chose this language is because we are interested in the following question. So now we start having commercial applications of quantum information technologies. So we have some boxes that are claimed to be quantum computers. We have in many labs, people are preparing machines that simulate other systems of scientific interest. You can buy quantum cryptography, you can buy quantum random number generators, and usually you're going to pay a lot of money for these devices, or you're going to make a very complex experiment to simulate something. And what happens here is that if you think about it as a user, all these applications are just boxes, okay? And you interact classically with these You lost the connection, right? Or I lost the connection. Hello?
Yeah, it looks like the host lost the
It
connection.
was my problem. Now I think it won't happen again. Sorry.
Yeah, sure.
So where was it? Was it here or before?
Yeah, I think this was here. Yeah.
Okay, so what I'm saying is that no, I have a problem with my mouse. Why is so slow? Sorry, I don't know what's going on. No. Okay, I will proceed like this. Yeah, so what I was saying is that you want to make sure that these devices behave as expected. So you want to know, this is a problem of quantum certification. Okay, so you want to know that this is a quantum computer, that this simulates a system, this is cryptographically secure, and this is quantum random. And the device independence language is very convenient for this certification question. And okay, I always use this joke. It's already many years that I'm using it, but I still keep using it because it describes very well what we want to do. So you can think of you as a user buying a quantum random number generator from a provider, and this is what you get. Of course, this is a box or a device, and I mean, they can claim that this is a quantum random number generator, and you want to make sure that this is a proper random number generator. Okay, so basically, we want to certify that this is a proper quantum random number generator from the statistics that we see in the box. Okay, so this is, again, this is the classical output, this is the black box device, and this is you as a user, and you want to make sure that this is a proper quantum random number generator. And more in general, from a certification point of view, you want to certify devices only from the outputs you receive from the devices. So again, this is why we are interested in this device independent scenario. Okay, so these are the devices. This could be the daemon that we saw in the previous joke, providing the outputs. You may be able to interact with the devices, and I think this is critical for what I'm going to say. And we want to say things from the observed correlations. So clearly, if these correlations can be explained by a classical model, then these correlations won't give you any advantage for quantum information processing. Okay, so you should observe non-classical correlations for a given setup to be useful in this language. Okay, so non-classical may depend on the system. In my case, since I won't make assumptions on the devices, this usually means that you should violate a Bell inequality or something similar to a Bell inequality. And a motivation for us came historically in the group from the hacking attacks on quantum cryptography protocols. So possibly you know about them. So several hacking groups of researchers, they were making hacking experiments. So they bought quantum cryptography devices from companies, and they showed that cryptographic solutions could be hacked. Okay, so Makarov was one of the most active researchers in this direction. And then if you think about what I believe here people know about quantum info, so you may know about BB84 protocol, the historical first proposed protocol. For BB84, we have a security proof that tells us that the protocol is secure, and there are no attacks. Okay, so then we should understand how come Makarov and other hackers could break the security of the protocols, even if there was a security proof. Okay, and what we understood is that what the hackers did, they broke the implementation of the principle, because when you define a protocol, you give a list of theory requirements for the protocol. So for instance, in BB84, you assume that Alice is preparing qubit states, and these states are in the X and Z and minus X and minus Z direction. And this is sent to Bob, who makes some sigma X and sigma Z measurements. And here you have the security proof, but of course, when you think about the implementation, you never meet these conditions, okay? So the states you prepare are prepared using a laser source, and a laser source for sure does not live in a Hilbert spectral dimension 2. And also you make measurements that are based on a single photon detector. And of course, a single photon detector is a complex object that is not an ideal spin 1/2 measurement. So the hackers hacked the implementation, despite there was a security proof in the theoretical side, because the two scenarios are not the same. Okay, so the implementation does not meet the conditions, does not perfectly meet the conditions that you have in the theoretical description of the protocol and in which you derive the security proof. So in a way, hackers, they don't care about the fact that there's a security proof, but because the security proof does not apply to the implementation. So this is telling you that if you have a gap here, especially for cryptographic scenarios, this may be a problem, okay? Because you will always be proving security theoretically here, but if there is a gap, this security proof is somehow useless for your implementation, okay? So if you require a lot from a theoretical point of view, this opens a security loophole for your description, okay? So what is the way of not having a gap between theoretical description and implementation? Well, the solution is to work on the device-independent scenario, okay? Because if your theoretical description is only in this minimalistic scenario and is only given by the correlations, then there is no gap between your theoretical description and implementation, because in the implementation, either you see the correlations you need to prove something, or you abort, okay? So, but you only go ahead with the protocols where you see the statistics that is required for your security proof, okay? And you don't make any modeling of these devices. Okay, so this is something that we proposed already 15 years ago. But this was also one of our motivations to work in this device-independent scenario, because you make protocols that are robust against previous hacking attacks. Okay, so then that was a sort of long introduction. I was telling you about why we care about networks, because we think it's interesting, and also it's becoming a reality. And then I was telling you that among all possible ways of studying networks, and I was going to do it in the device-independent scenario, because it's a good language for certification and also to construct protocols robust against hacking attacks. So the first thing I have to do, I have to characterize the objects I'm going to deal with, these correlations. And this is what I'm going to tell you now. So, and for that, I will use something that was some ideas that were already introduced in this paper by Branciard, Gisin, and Pironio. So some of they consider this one of the simplest networks that exists, which is the one associated to entanglement swapping. So there, what you do, you have a state of two particles that is sent to Alice and Bob, and another state of two particles that is sent also to Bob and Charlie. And now if you think about the quantum mechanical description of the experiment, it's the one you have here, okay? So you have a measurement for Alice, another measurement for Bob, another measurement for Charlie, and the two states, Alice B1 and Bob2 Charlie, okay? And you put tensor products because of the network geometry, okay? So this preparation is independent from this preparation, and these three measurements are independent, and you combine everything with the Born rule. So these quantum correlations, we want to understand which correlations do not have a classical analog. Historically, the way we did that was you compare these correlations to what you can obtain with classical correlations, okay? And if you follow the EPR Bell reasoning, then you have these local hidden variables that go to the parties, and then the output is produced given the hidden variables and the input in all the three parties. But if you think about the network topology, this configuration does not make much sense, because it's like if the same lambda was produced by the two sources. You see here, Alice is providing the output given the input and lambda, and Charlie is doing the same, okay? But it doesn't make so much sense that these two people use correlated instructions, okay? Because they receive states from two independent sources. So what they propose in this paper is like, let's study this in something that resembles the network topology. So you have two independent preparations, and then this is the relevant set of classical correlations. So what we want to find are quantum correlations that cannot be written in this classical form, okay? And then we will say that we have quantum correlations that do not have a classical analog in the same network topology. And for that, then people realize that you can make a nice connection between this problem of characterizing correlations in network and the language of causal networks. Okay, so what is the language of causal network? This is what we use to infer causes between observed correlated random variables. Okay, so just for you to understand, so we have a group of people, say, that smoke, and another group of people who have lung cancer. Okay, and we see that these two variables are correlated. Okay, so a standard question to understand correlations and in science is to understand which causes are behind some correlated events. Okay, like having cancer and smoking. Well, we usually tend to say that if you smoke, you have cancer, but as you may know, I mean, just from correlations, you could also explain this as if you have cancer, you tend to smoke. This is a valid possibility. The two possibilities are compatible with the observed correlations. Or there's even another possibility that perhaps it's also valid, is that, okay, there is a hidden variable you didn't observe, which is that people get nervous. And people who get nervous, they tend to smoke and have cancer. Okay, so you see here with this language of putting boxes and arrows, I'm describing, you encapsulate in a very intuitive and pictorial way how you describe causes giving rise to correlations. Okay, so this is the language of causal networks. So you work with directed acyclic graphs. So you have, oh, there's a typo here, sorry. So you, the observed variables are represented by circles, like smoking and cancer. If you need hidden variables, because you may think that it was a variable that was relevant for your problem, but you couldn't observe it, I would put squares, like this, being nervous. And then you put these arrows, no, just to represent the causes. And people realize, in particular, I think Tobias Fritz was very, he made very nice contributions into that this is the language you have to use to describe correlations in networks. Okay, so let me go back to the simplest Alice-Bob network that you use in Bell theorem. So you have a state being prepared, and you make these different measurements, and you get these different outputs. Okay. So what is this? How do you describe this with causal networks? Well, I mean, you have some hidden variables that were prepared. I mean, hidden particles, hidden correlated particles. Okay. And this was sent to Alice, and Alice also received another observed variable, now X, and she produced an observed variable A, depending on X, and what came from the source, and the same for Bob. So these are two identical scenario descriptions of the same scenario. And now what happens, Bell theorem, you can reinterpret it as saying that there are correlations between observed variables that you can not explain with a given network if everything is classical, but you can explain with the same network if you replace classical hidden variables by quantum hidden variables. Okay, so you see, I mean, it's the same causal network, the same network topology. The only difference is that this is the source is producing classical particles or quantum particles. So this is telling you that the causal explanation of some observed correlations may vary depending on whether you're dealing with classical or quantum information. And then once you understand this, okay, you can simply map any Bell scenario with this causal network. So for instance, the bilocality scenario entanglement swapping, okay, in which you have these two independent sources. Well, you see, now the inputs become these observed variables, the output is a second observed variable, and you put the arrows, okay? So the output here depends on what came from the sources, and the input is what is also happening in the more standard physics representation of the experiment. So there is a one-to-one mapping between the two scenarios. So we want to understand correlations in network. We understand that this is connected to the directed acyclic graphs using causal networks. Now let's try to do it. And also this is relevant. I mean, I gave this motivation from a quantum information point of view, but it's also relevant if eventually you're interested in understanding quantum effects in experiment. I mean, causal networks is used in many disciplines, and people want to understand, okay, I have these observed correlations, how I can explain them. Okay, so I think it's plausible that in the future, in many of these disciplines, people will start caring about quantum effects. And then we know from Bell theorem is that the tools we have to understand causality in networks vary depending on whether we use classical and quantum information. So we have to understand tools to understand how causality is affected by quantum information. Okay, so there are books about causal networks, but of course, all these books, they only care about classical information. So these books will have to add chapters on how causality is affected by quantum information. And this is a difficult problem because also it's difficult for classical systems, okay? Because usually in causal networks, the set of correlations you care about are non-convex, okay? So this happens for, this is also very, a rather famous network in quantum information processing, the triangle network, in which 3 bipartite states are prepared and they are sent to 3 observers in this triangle configuration. So this is the classical network where you put, say network with classical information, everything is classical. And we can also, and the correlation that you can achieve with this configuration is non-convex. Okay, and this makes the problem quite hard. And now if you think about quantumly, we only have to replace this by quantum states. And it's a larger set, but it's again non-convex. Okay, and because of non-convexity, these sets are harder to characterize. I'm not going to give you details about this, but we wrote some papers and we are still interested in finding good methods to characterize the set of quantum correlations that are achievable in different networks. Okay, so if you are interested, look at these papers or ask me later. There is still room for improvement. We presented the first methods here. They can deal with small networks, but as soon as the network becomes large, it's a very hard problem. Okay, but at least we have some tools that tell us about sets of classical and quantum correlations, and these tools can be implemented in small networks. Okay, so now, after motivating, explaining what we care about, and explaining the language we use and the tools we use, now let's look at possible results that we got with this in this framework. Okay, and my first result will be on foundations, and then I will tell you about results more connected to quantum information applications. Okay, so this is a result that we published last year with Marc-Olivier Ranou, who is a postdoc in my group, and a list of people. Maybe I should have written here who was in the paper, but there was people from Geneva, Nicolas Gizan and Armin Tavakoli, who maybe at that time was in Geneva or moving to Vienna, and Miguel Navasquez from Vienna, and students and postdocs from his group. So what was the motivation here? So we wanted to understand what the role of complex numbers in quantum theory. As you see, this is pure foundation results. Okay. So what I mean by this is that if you open a textbook in quantum physics, you will see that in the standard Hilbert space formulation, you have a series of postulates that are described in the theory. Okay, so you have, well, you say that to any physical system, you associate a complex Hilbert space. A state is a vector in this Hilbert space. Measurements are given by projectors. You compute probabilities with the Born rule, and whenever you have different systems, you use the tensor product to combine different systems. Okay, so this somehow we take for granted. In particular, we take for granted that the space is complex. Okay, and I think this is, maybe we are used to that, but it's a bit weird, no? Because it's really one of the first situations in which complex numbers appear in the, I think it's the only example we have in which complex numbers appear with a fundamental role in the definition of a physical theory. Okay, if you think about classical mechanics or electromagnetism, you never use complex numbers in the definition of the theory. Maxwell equations or the Newton equations, or they're never described with complex numbers because they refer to real quantities. Okay. In quantum physics, we use the wave function. It's not clear if the wave function has any reality. And in particular, if it was, you may doubt about it because it's something that for which you need complex numbers. Okay. So yeah, it's the first time that we found a theory that is really openly stated in terms of complex numbers. And actually, this was something noted already by the fathers of the theory. So there's a letter from Schrödinger to Lorentz, in which he was wondering whether psi was really complex and whether in the end it had to be a real function. Okay, so perhaps the intuition was that complex numbers sometimes are used for mathematical convenience, but we know some of their description of reality is always in terms of real numbers. Okay, so the question we wanted to understand is what happens if you replace complex number by real numbers. So what I'm saying is that you take the same theory with the same postulates, okay, in this Hilbert space formulation, and then you replace complex by real. And we wanted to understand what is the new theory. Is it a new theory? Of course, it cannot be more powerful than the previous theory, but is it equally powerful or less powerful? Okay, and we're not the first ones considering this question. For instance, there is a nice paper where this is described, but okay, this question has been considered by many people before us. Okay, so we want to understand whether this innocent step has experimental consequences. Okay, so you should understand that what I'm going to do now is you can understand as a game, okay? There is a physicist, a complex physicist who believes in complex Hilbert space quantum theory, okay? So this physicist, she believes that she's dealing to describe the quantum experiments with Hilbert spaces, you need complex numbers. And on the other side, there is a real quantum theorist who believes that this is just for mathematical convenience, but you can arrive at the same predictions using real operators, okay? So now the complex physicist has to prove the real physicist to be wrong. And for that, we have to do the same as in a Bell theorem, okay? We have to construct an experiment and produce correlations that cannot be replicated in the alternative theory. Okay, and of course in this, I have to exclude any possible explanation in real quantum theory. Okay, so dimension does not play any role. So the complex quantum theories provides an experiment using qubits doesn't mean that the real quantum theories has to provide a description of the same experiment using, say, real bits. Okay, because if you fix the dimension, we know that there's going to be a gap because, I mean, to describe one complex number, you need two real numbers. Okay, so it cannot be with the same number of degrees of freedom. Okay, so I hope it's clear what I want to do. So the complex physicist has to falsify the model by the real quantum physicist. Okay, so if you start with the simplest experiment, in which you prepare states, okay, and you make measurements. Okay, I'm going to do it for a single quantum state preparation and a single quantum measurement, but this argument is valid for arbitrary preparations and arbitrary measurements. Okay, what you will see is the probability of observing a given result will be written as the trace of the measurement acting on the result, on the state. Okay, so the complex quantum theories thinks of an experiment in which all these objects here are complex. Okay, now the real quantum theory has to replicate this, has to explain it with real operators. Okay, so what he does, he takes a Hilbert space, he doubles the dimension of the Hilbert space by appending an extra qubit. Okay, so the tensor product has now dimension these operators were acting on a space of dimension d. The new operators will act in a space of dimension 2d. Okay, and now in this extra qubit, we are going to use the eigenstates of sigma y, okay, which are given here. Okay, so plus I and minus I. I'm not saying that you are going to prepare these states. I'm going to use them, but you will see how I'm going to use them. So what the real quantum theorist does, he takes the states prepared by the complex physicist, and he constructs a new state, rho tilde, and new measurement, pi tilde, in this form. Okay, so you can see that this state and measurements are real because if you take the complex conjugation, this rho goes into rho complex conjugate and I goes into minus I, okay? And this is symmetric. So you get the same state. So rho tilde is equal to rho tilde complex conjugate, and the same for the measurement. And this is positive and it's normalized. You can see that this is a valid quantum state. Now, if you compute the probabilities here, and because probabilities are real, so probabilities are equal to the complex conjugate, and these probabilities are equal. Okay, so you can explain the same probabilities with this complex operator or with these real operators. So there is no way that you can falsify real quantum theory in such experiment. Okay, so maybe we're a bit too naive, thinking that a simple experiment like the one here could falsify real quantum theory. Let's try to think something more a la Bell theorem. Okay, so you prepare a state of many particles and you send to different observers, and these observers will make a measurement on this large entangled state. Okay, so I'm going to represent this in the case of Alice and Bob, but again, all what I'm going to say is valid for an arbitrary number of measuring devices. Okay, so these are the probabilities you see. It's just measurement for Alice, tensor product measurement for Bob, and rho AB. So, okay, maybe here you gain because before I was putting an extra qubit, but now you don't know whether to send the extra qubit to Alice or Bob. Okay, but still the real quantum theorist can reproduce everything because what the real quantum theory does, he appends an extra qubit for each particle, and he sends these particles to the new Alice and Bob. And basically what you do is like the state, you play the same trick, but these extra qubits are all correlated in the state I and minus I, okay? Now you can see that this state is real using the same argument as before, okay? You take complex conjugate, you get the same state. And now this measurement, you do the same, but now with just a single system I and minus I, okay, because only one qubit arrives. And again, this is real. And believe me, if you recompute the probabilities of making these measurements on this state, you will get the same numbers as the complex physicists had making the complex operators measurements acting on the complex state. Okay, so again, the real quantum theories can always find an explanation to the experiment, so you cannot falsify real quantum theory. Okay, so what we had is like, let's do something. Okay, this was published in 2009 by McCaig, Mosk, and Gizan, and somehow it seemed that you may have reasons to prefer complex numbers based on mathematical convenience, but there won't be any situation in which you will, I mean, any real quantum theory can provide an explanation to any quantum experiment. Okay, so there is no way of falsifying real quantum theory. But okay, what we realize is that if you go to a network, things become much more interesting. Okay, and basically what happens is that if you go to this entanglement swapping network, you can falsify real quantum theory. Okay, so the complex quantum theories will construct some correlations which are given by what we do in quantum physics. Okay, so there's a state here, tensor product, another state here, measurement here, tensor product, another measurement here, tensor product, another measurement here. And of course, this tensor product is essential for what I'm going to say, and it follows from the network geometry. Okay, so we are constructing correlations compatible with the causal constraints, the network constraints. And we could design in this paper, we give complex operators that you put here, you get some correlations. And you can prove that if you replace all these operators by real operators, you cannot get the same numbers. Okay, so there's a way of experimentally falsifying real quantum theory. And after our proposal, there were 2 experiments. We collaborated in this experiment in 2 groups in China, where they proved they got these correlations that do not have an analog in real quantum theory. Okay, so that was on foundation. So I was here. You see, there is an application in which, if you stay in your standard Alice, Bob, or even more parties language, but with a single state being prepared, you cannot falsify real quantum theory, as proven in this paper. But things become much more interesting as soon as you have this network with 2 independent states and 3 independent measurements. Okay, now what about applications? Well, something we were interested also is like whether we can, for instance, reveal the non-locality of a single photon in this using networks. Okay, so by this I mean the following: what is the single photon non-locality we want to reveal? Okay, if you send a single photon into a beam splitter, the resulting state is 1, 0, and 0, 1. So these are spatial modes. Okay, so the photon can take this path, and then you have 0 here, or can take this one, and then you have 0, 1. Okay, and this is what I'm representing here. So it's a very simple sort of entangled state that you can prepare, but of course, the problem is how to detect the non-locality of this state. Okay, well, there's an easy way of doing this, sort of easy way, for instance, theoretically easy way, which is you send the 2 modes into 2 atoms, and then you get ground excited plus excited ground, and then you can make measurements on the atoms, and you can detect non-locality. But we are interested in detecting non-locality just with standard quantum optic tools dealing with light, okay, without making this transition from light to massive particles. So what we did, I didn't update the reference. What we did in this paper with, well, Paul is a student, Abhi is a student in my group, and people from different groups again. So what we prove is that if you make a network made of single photon entangled states, you can have correlations that do not have a classical analog. Okay, so we designed an experiment in which you send the 3 copies of this state to Alice, Bob, and Charlie, who were making these photons or modes to interact at the beam splitter and making standard photo light detector, not photon counting, just photo light detector. And we were getting correlations that cannot be explained in the same network using classical information. Okay, so we are revealing the non-locality of the single photon entangled state. And another situation in which we think that networks can be relevant is just to make device-dependent quantum key distribution. Okay, so in device-dependent quantum key distribution, what I was telling you is that you want to make crypto based on correlations between Alice and Bob. And here you have to see a Bell inequality violation, okay? Because if you don't see a Bell inequality violation, you have a classical explanation for these correlations, and you cannot get any quantum information advantage in the device-independent scenario. So then the problem is that you have to see a Bell inequality violation between two distant parties, Alice and Bob, and this is difficult. Okay. So why is it difficult? Well, I'm going to skip this for the sake of time, but basically it's difficult because there are losses. Okay. So when Alice and Bob try to make a Bell test, say because a source prepares an entangled state and these particles go from the source to Alice and Bob, in most of the time the photons are lost. Okay, then you have losses that are pretty large, and this really creates a problem, because if you have losses, this is like having imperfect detectors, and you know that then we have something called a detection loophole, and we cannot have a proper Bell violation. Okay, and this will happen no matter what. Okay, because there will always be losses. I mean, for instance, in fiber optics, light intensity decrease exponentially with distance. Okay, so there will always be losses. So you want to do device-dependent quantum distribution between two distant parties, you have to find configurations in which you know how to fight against losses. And then in particular, a point-to-point configuration will never work. Okay, if you prepare a state and you send it directly from Alice to Bob in a point-to-point configuration, I mean, since you will have to send light at the single photon level, the photon will get lost and you cannot run the protocol, because the correlations can always be explained by a classical model because of the detection loophole. So a solution for that is like you make some sort of quantum non-demolition measurement. Okay, so the idea is that you prepare a state, okay, you send it, and you only you see whether the photon has arrived. And if the photon has arrived, green light, then you make the Bell test. So this is a way in which losses become irrelevant for the security of the protocol or for the proper Bell inequality violation. Okay, so there is no detection loophole if you are able to monitor that the photon arrived and then make the Bell test. Okay, all the losses that take place from the propagation to the, say, non-demolition measurement is just a trigger that tells you that you can make the experiment, are irrelevant. Okay, or you can make some sort of central heralding in which these people prepare two sources, they send to the central location, and you have some sort of swapping experiment. Okay, and only when this works, you know that you run the Bell test. Okay, so these are configurations that allow you to forget about the losses in the channel and have a device-independent quantum distribution protocol. Still, I mean, it will be difficult because you also need very clean labs, but it's a possibility at least to remove channel losses in the implementation. So a way of doing this is as it was done in the first loophole-free experiment by Hanson, or Monroe did in previous experiments in ions, or by Furter. Actually, I believe I forgot a reference because there have been, sorry, this is a mistake. There have been device-independent quantum distribution implementations last year by Furter, Scarani, Lim, and co-workers, and also by Sanguar, Renner, and co-workers using this. I'm sorry, I forgot the references. Using this geometry. Okay, so you prepare atoms or ions. You prepare atom-photon entanglement. So here you have a photon that leaves and is entangled with the atom, and here you have sometimes a photon that leaves, and you make an entanglement swapping experiment. So only when you detect here the right clicks, you know that photons were produced and were entangled, and you make swapping. So now the atom particles get entangled at distant locations, and you can make the Bell test. So this works. I mean, it has some problems for scalability because the rate of this process is very slow. It's very low. Okay, so the process is slow, and okay, you can potentially put also the photons are emitted everywhere unless you put a cavity. So these are difficult experiments, although there have been proof of principle demonstrations. So what we want to do, and also some other people did, is, okay, let's try to think about a purely photonic experiment. Okay, so that was, for instance, proposed in this paper by Gishan, Pironi, and Sanguar, but actually, I mean, the security proof is not completely valid that they give in this paper. So I'm not saying that maybe the protocol is secure, but not with the security proof and with the rates that they compute. And what we did we also published another paper in which we showed that single photons may give an advantage in this configuration. Okay, so we gave two geometries. I don't have time to explain these geometries, but basically, I mean, you can think of parametric dark conversion, but single photon sources give you an advantage in which, okay, you prepare these single photons and you make some operations with them, and you only look at the outputs produced by Alice and Bob when you have a given click here. So this is the heralding process that tells you when to take the output of the bell test. Okay, and you can also remove channel losses, and the rates you may get are of the order, asymptotic rates are of the order of tens of bits per second already at around, sorry, no, this is the right cursor here. So, or there's around tens of kilometers. Okay, or 50 kilometers, you have around 1 bit per second. Okay, so the conditions are, we are improving now these numbers, but okay, I think at the moment with our knowledge, getting rates beyond bits, tens of bits per second at tens of maximum 100 kilometers for device-independent QIQT is really a challenge. So here there's a nice problem to think of. And again, you cannot do direct transmission. Okay, you have to think about small network to make this device-independent QIQT protocol work. Okay, so with this, I arrive to the conclusion. So, well, first thing is that we're interested in small quantum networks because they are happening. And we know that you may get some new physics, some new effects there that you cannot get in the standard Alice-Bob configuration. Okay. So we know that you can, as I say, I showed this in the case of complex numbers, but there are several situations in which they give you an advantage compared to standard configurations. So I think it's interesting to understand what you can gain from these small quantum networks compared to standard Alice-Bob networks. And just for you to have a list of open questions. So I didn't talk about this, but there are situations in which you have bipartite objects that are useless. For instance, the situation we have in mind is a bell test. So we know there are some entangled states that don't violate an Bell inequality violation. So bipartite states. So Werner states, they were really invented to demonstrate this. So it's a state of two particles that cannot violate any Bell inequality in the standard Alice and Bob configuration. But we know if we make a network made of these bipartite states, so I make a network where there are different observers and they are all connected by this bipartite state, I may be able to violate a Bell inequality. So we have examples of that. Okay, so in a way, the network activates the non-locality of the state, or as it happened for the single photon state, we don't know how to detect its non-locality if we do it in the Alice-Bob configuration, but we know how to detect it in the network. Okay, so I think it would be nice to find really simple examples of network activation. Okay, so and even demonstrate this effect in the lab. I think also from the point of view of foundations, okay, we need methods to characterize these sets. Maybe not precisely, but methods that at least provide some answers for large networks. Okay, so we need to improve the scalability of the methods we have. And then one of my obsessions is like how to apply these tricks to improve the protocols for long distance entanglement distribution, and in particular, then how to use these entangled distributed states at large distances to make device-independent quantum distribution. Of course, if we have a quantum repeater, then we can make long distance entanglement distribution and device-independent QIQT. But here I'm thinking of methods that could eventually work before having a quantum repeater. And I think that's all from my side. Thank you very much for your attention.
Thank you, Professor Acin, for a very nice comprehensive survey of various issues associated with quantum networks and sharing information and correlation over quantum networks. We have time for some questions. I request people to type any questions that they may have in the chat. So while we wait for questions, maybe I can start off with one of my own. Have you looked at questions of noise in these quantum networks? Like how would decoherence affect these device-independent protocols, or how would they affect the extent of correlation that you can share over these networks? Do we have studies on that?
Yeah, yes, we have. So we have studies. So for instance, if you think about say, well, of course, I mean, this is a very generic question. I will tell you a few examples of where these things have been studied. No? So we think about, for instance, what I was telling you here, an example of network activation. Here, you care about noise. Okay, so if you think about a Werner state of 2 qubits, This is a maximal entangled state mixed with white noise. Okay, so now people have a good understanding of when a noisy maximal entangled state, which is Werner state of 2 qubits, violates a Bell inequality. And what people have seen is that the amount of noise, the threshold, the noise threshold gets better if you make this network of these states. Okay, so it's the same bipartite state, but you need many, and you need to make the network. Of course, you may tell me now, okay, is it worth paying the effort of preparing all these entangled states and making this complex network just to gain maybe a few % of noise tolerance? Probably not. Okay, but we have tools to do this, to study correlations in the presence of noise. What will happen, of course, is that the noise is very large, you will lose this effect. But we have also some examples in which the network geometry was increasing the robustness. Okay, the fact that you have this more network. Of course, again, if the noise robustness improves by 10%, and if for that you need a network with entangling measurements, maybe the effect is not so good. Okay. Also for device-dependent QKD that I explained, people have studied the effect of decoherence like QBER, quantum bit error rate, on the security of the protocol. And these protocols are relatively, I mean, I think the robustness against the coherence of standard crypto is around 11%, and the robustness of device-independent QKD is around 7%. Okay. So I think it's more or less the same level. So the killing factor for device-independent QKD are losses, which is it's a sort of noise, but a bit different from the coherence, I would say. But yes, we have, with the tools, we have a good understanding of how to deal with noise and how to characterize noise. Yes.
Nice. Thanks. Any questions from the participants? Professor Dipankar Home has raised hand. Please go ahead.
Antonio, thanks for the lovely talk. I'm Dipankar here. So nice to see you after a long time. So you mentioned about network activation application in the context of showing non-locality for states which do not exhibit Bell violation. So can you give some example of some work, which, not just increasing the noise tolerance from that point of view, but from showing the violation of Bell for states which do not violate Bell by usual criteria for the bipartite states.
Let me just, maybe I'll look for another presentation I have. Let me see if I can. Okay. I think I have something that I gave recently. Let me see if I find it. Yes. Okay, so this is what I was saying. No? So if you take a Werner state of 2 qubits, this is maximum entangled state with white noise, okay? And now you look at when these states violate a Bell inequality, okay, as a function of the noise, okay? So around 1 square root of 2, they violate CHSH, and then this has been improved, okay? So in this region, they violate a Bell inequality. And now what we know is that these states don't violate the Bell inequality where the noise is large, okay? So which means that the singlet fraction is small. Okay, so here the state is separable. So here it's entangled, but they don't violate any Bell inequality. Okay, so this we know that here, this is for general measurement, this is for projective measurements. Okay, so what we did in this paper, okay, maybe I have it here. Yes. So we took a network, a star network, in which there were, I don't know, like n parties, and they were all sharing 2 qubit Werner states. And then we look for a Bell violation in this. This is we call it a network state, but the network is only made of copies of the bipartite state. Okay, so in a way, you are studying the properties of the bipartite state, although you do it in a network, okay? And then what we could see is that for a network larger than 21, okay? This is why I'm saying that it's not practical, it's more fundamental what I'm telling you, okay?
Okay.
You can see a Bell violation here, where we don't know how to see a Bell violation in the standard network. So this is what I'm saying as an example of Bell violation or activation through the network. So okay, because the network is only made of bipartite states. and you see something that you couldn't see in the bipartite network.
But that was in 2011. After that, no improvement in reducing the
Yeah, this
number
is
n
frustrating.
or,
Yeah. This is frustrating. We got the result, and you see, I mean, we needed to go to 21. And in this, yes, and here we were testing when we say Bell variation, we really meant standard Bell non-locality, in which, if you remember my talk, there was only one lambda, some classical variables. Okay, but if you have a network, you should put lambda, mu, sigma. Okay, so you can only win by making these extra requirements to the classical model. Till, I think this is the best result I know in the market. Since more than 10 years. So it's frustrating. I've been working a lot on this.
Yes,
with no success.
Okay. Thank you. So lots of work to be done, especially that long distance entanglement.
Yeah, but even as a purely foundational question, no, like I don't know, can we get down up to the separability region and see some sort of non-locality activation?
Yes,
okay, this is open.
Yes. Thank you.
Thank you.
Yeah. I think there was one more raised hand. I request the participant to go ahead and ask the question.
I'm not sure if it was Dipankar. Okay, something.
I think there's one question in the chat. Maybe I will just read it out. So this is about, okay, so maybe I'll just quickly read out the question and then we can stop with that. This is Abhishek from ICER. I have a question on correlations stronger than quantum correlations. It was asked if nature supports stronger correlations than quantum. So does your hierarchies have any significance in terms of your nth hierarchy is a set of correlations conforming to certain set of basic assumptions on nature? I don't know if you understand the question.
I think I can say a few things about this.
Okay.
So yes, maybe I'll go back to the presentation. Yes. So, well, already 15 years ago, we invented a method to characterize the set of quantum correlations in the standard Alice-Bob configuration. Okay, so here I was representing the set of classical and quantum correlations for this network. Things are not convex, but before that, we were just studying these sets, classical and quantum, for the standard network in which you only have, say, Alice, Bob, and rho AB. Okay, forget about this part. Okay, so this is the standard Alice, Bob situation. And we gave this MPA hierarchy that is given the set of quantum correlations, which is simpler in this case because it's convex. And this is useful because with the MPA, you could also study theories beyond quantum correlations, okay? Because you have a better characterization of the quantum boundary, so you can also study things outside the quantum boundary. So now we can try to do the same, also try to find ways of bounding the set of quantum correlations by taking into account the network geometry. In a way, this is what we did in this paper. So this paper, well, in the two, but especially in this paper, it's called, we gave a method called quantum inflation that basically, one of the elements we use in the construction is this MPA hierarchy. So these type of constructions are still, make still a lot of sense in these networks. Now, what I can understand as the second part of the question is what happens if these theories in networks? And this is a very interesting question. So there was a very nice paper by Miriam Weilemann and Roger Kolbeck, in which they studied some theories, some GPT theories. Some of them were given in the Alice-Bob configuration correlations stronger than quantum physics, but they were not given, but quantum physics was given stronger correlations in networks. Okay, so I think studying theories in networks beyond Alice-Bob, okay, it's a very good question. So I don't know, it's difficult, but it's a very good question because once you have a network, you have entangled states, but you also have entangled measurements. You have entangled preparation and entangled measurements. And then in GPT theories, we know that there is a trade-off between what you can prepare and what you can measure. And then things become quite interesting. I mean, it's difficult. If you're interested, look at this paper by Lehmann and Kolbeck. And things are quite open. So I think it's a very good question to study.
My question was that because your nth level NP hierarchy has any significance in terms that they conform to some assumptions that we expect of nature, certainly more than no signaling that we don't find in quantum physics. If you can hear me.
I have some problems with the sound. I don't know if it's only me.
He seems to ask whether you need assumptions more than just no signaling in order to...
In networks?
Yeah.
Yeah, okay. So the hope, let's say, is that... okay, what is no signaling on a network? Okay. So no signaling, if you think about network, in the Alice and Bob network, no signaling are just the causal constraints coming from the network. Okay, what I mean is that in Alice and Bob, this is the network that you use to describe Alice and Bob. Okay, so the constraints on these correlations coming from the network geometry are the no signaling conditions. If you go to more complex networks, you have some other conditions that are the equivalent of the no signaling constraints. Okay, but you should understand that here we have a more complicated or a richer geometry, and you have some other constraints. So already characterizing the analog of no signaling constraints in networks is interesting. And now the hope is that those generalized no signaling constraints are enough somehow to single out the quantum theory. Okay, but this is the hope, but we are very far from this. Okay, this could be this is an interesting research problem.
Right. Thank you so much, Professor Acin. And I think